Hello folks, and welcome back to another episode of Long Branch Never. Today is finally the day we will be writing our first lines of assembly code. The application we'll be working on at first is a Hello World app, and I plan to break this up into two separate episodes. I know that might sound a little bit odd for a simple Hello World app, but as I started getting into the content of this episode, I realized that there was a lot here and decided to split it up. My goal is to keep these somewhat short, hoping that they're easier to follow, and I don't want to overwhelm folks with too much information, making these too long. So one of the things I wanted to do first before we got into the coding portion of the episode is a little bit of housekeeping from last episode. So one of the things that we did is we set up our Notepad++ application, and as I was going through putting the user-defined language in, I realized that the asm.bat or the batch file wasn't properly formatted. And the reason for that is because if you go into styles or settings and style configurator, if you look at the one that we had initially picked, the theme that we initially picked, we had chosen Ruby Blue. And for some reason, that is not compatible with batch files. So if we go into the style configurator again and change that to Monokai, another one that works well is the Vim Dark Blue for Linux folks. They'll be very familiar with that. We'll change that to Vim Dark Blue. That works as well, but we're going to stick with the Monokai, and it looks just as good. The formatting and the color coding actually reminds me of Sublime Text for those folks that might use that as a text editor. One other thing that I wanted to let folks know is we left this 6809 assembly.xml file on the desktop. We don't need that any longer because it actually has been imported into our user-defined language XML file in our profile within Notepad++. So we can go ahead and get rid of that. You do not need to leave that on your desktop. So with that out of the way, let's take a look at what we're actually doing with assembly code. So one thing you want to keep in mind is that we're working directly with hardware, and in particular the CPU. The CPU is comprised of several registers, which you can think of as very basic, extremely fast logic units. They do things with small bits of data very quickly. Some of the things that you might be doing are fetching data from a location, typically memory, storage, other CPU registers. You process that data, and then you put that data back into memory, storage, or other CPU registers. Now, the way you think about this as far as building code, we do this over and over again, building simple logic units. Then we correlate that into code snippets, build that even further into functions and subroutines, and then that actually builds into full-scale assembly language applications. Okay, so as we get into this, there's a couple things that you're going to need to become very familiar with as you begin coding on the 6809. The first of those is becoming familiar with the architecture of the 6809, and in particular, the registers of the 6809. So let's go ahead and take a look at those. So first we have two 8-bit accumulator registers called the A and B registers. Each one of these are capable of holding a value from 0 to 255, or they can be combined together to form the D register, which forms a single 16-bit accumulator able to hold values from 0 to 65,535, 64K basically. Next we have two index registers, the X and Y registers. Again, these are 16-bit, able to hold values from 0 to 65,535. Think of index registers as being used for position tracking, and in our case, typically they're used for keeping track of positions in memory. Next, we have our stack pointer registers, which are very similar to the X and Y registers, or index registers. The S and U are used as stack pointers. Again, these are both 16-bit registers. These are typically used for storing temporary values in a stack form that you're going to reference again later in your code. You typically push things onto the stack, and then you either pull or pop things off the stack. For the 6809, it's actually a pull instruction. We'll get into that more in later episodes. Next, we have the PC or program counter register. This points to the next instruction in memory. It's basically tracking where we are in the execution of our code. Next, we have our direct page or DP register. It's used in direct addressing modes. We'll get into this in later episodes, but think of the 64K memory space of the Coco as being broken up into 256 separate pages, with each page being 256 bytes. The DP register more or less allows us to specify which page of memory we're addressing at that point in time. It's typically default to 0. And then last, we have our condition code register. The condition code register is broken up into 8 separate bits, which are used as flags, typically true or false, on or off. These flags are used for basic decision making and branch instructions, as well as turning on system interrupts on or off as well. But we'll get into that in future episodes as well. In today's episode, we'll be using only the A and X registers. So something else that you're going to need to become familiar with as you get into assembly coding is the memory map. Now here we're taking a look at the 64K memory map for the TRS-80 color computer. It starts at address 0 and goes all the way up to hex address FFFF. This gives us 65,536 bytes of addressable memory space. Now, understanding the memory map is important to assembly coding because you need to be fully aware of where you're putting your code as well as data into this memory space, and you also need to be fully aware of how your code interacts with other areas of system memory. Very often this is the video memory space. So we will be focusing on the video text or the text video screen portion of memory today, which starts at address hex 400 and goes to hex address 5FF. It's 512 bytes long. One thing to also keep in mind as I'm going through these tutorials, I'm going to be using hexadecimal notation through much of the tutorials, especially when it comes to memory addressing. It's going to be good for you to practice and brush up on hex notation, and it will become easier and almost second nature for you. You'll also see how much it really applies to assembly coding as we go through the tutorials. So let's take a closer look at the video memory space. So we'll zoom in here, and what we'll do is we'll overlay the memory map and the memory locations onto the video text screen. So as you can see with the overlay on our text video screen here, we have in the upper left corner memory space starting at hex address 400 with 32 columns across and 16 rows down, ending in the bottom right corner at hex address 5FF. So now let's go ahead and get started with some coding. So what I'm going to do is I'm going to browse to my 6809 assembly code folder on my desktop, and I have a template here that I've already started. You can go ahead and download this in the show notes below, and basically what this is it's just giving a place for us to get started with our code. Up at the top I have my comment section, which I typically have on every single piece of code that I write. It gives a brief description of whatever the code is, or subroutine or function in that particular case, and it also will give inputs and outputs to that section of code. So if it's a function or subroutine, it's good to know what you're going into to the code with, or to that routine with, and what you can expect for outputs. Now, one thing to keep in mind, I do want to mention, assembly language coding does not have a strict format structure, but there are some rules that you need to adhere to, or else the code will not compile. So one of those rules is that you need to have your code broken up into 3 separate columns. You can use a 4th column for comments, but at the very core, you need to have 3 columns. The first column is over here where I have my start statement. And this column is the instruction label column. Now, instruction labels are optional when you're coding in assembly language, but they are quite useful as you are trying to focus on developing position-independent relocatable code. That is, if you're trying to move that code around to different memory locations, it makes it much easier where you have relative addressing in place versus a strict absolute addressing in place. Our second column here, where you see this org statement and this end statement, this is our opcode column. or this is where the assembly language commands go. This is often referred to by old school assembly coders as the mnemonics for assembly coding. And then our third column here is for our operands, which are used by our opcodes for interaction with data, memory, other registers, and branching locations as well. So this is the crux of what you're going to start with pretty much every assembly language program that you write. So it's nice to have this as a template as you get going. So a couple things that I wanted to mention about why I have these statements here and what we're starting with. The org statement is typically going to be part of every single piece of code that you write. And what the org statement actually does, it's a compiler directive that's basically telling the compiler, this is where I want my application to start. This is where I want my code to start in memory. And I have mine starting at hex address 4000, again referencing the hex notation in the coding. So 4000 is actually a fairly decent place to start. It's a fairly safe place to start. It's actually right in the middle of our memory map and address space, and it is just above our 8 pages of graphics memory. You can go a little bit lower and still work with graphics, but 4000 is right at the upper top of our 16K going into our 32K memory space. The start label that I have here is also very important. And what that does is it actually tells the compiler, or in our case, where we are starting our executable code. That is, when we're writing our code, what address space is going to be the executable portion of our code. So in this case, we're going to be starting at address 4000. So if I put my first command here, that's where we're actually going to compile and start executing code. Lastly, we have the end statement, and the end statement is extremely important because that basically tells the system that that's where you want to stop executing. This is the last point in your code that you are going to execute. Without it there, it would continue to execute beyond that, and it would just produce garbage or just halt the system. And we'll show an example of that as we get going. And again, I have a start statement here at the in the third column for my end statement. And again, that's just telling the compiler that that is where the program is going to end, but I want to reference the start position as the first address that we're going to execute in our code. And I'll show you examples of omitting that as well. And you can see the behavior as we get into coding. Okay, so let's write some assembly. Okay, so to get started, what we need to do is try to understand exactly what we're telling the computer to do. And in this case, we're doing a Hello World app. So essentially what we're doing is we're loading some text characters into some memory space, and then we're trying to output those to the video text screen. As I mentioned earlier, we're going to be using the A register. So what I'm going to do is I'm going to load A, the abbreviation for that is LDA, with some value. And for us to write Hello World, what we need to do is load the first character of our text into memory, or into the CPU, the A register in this case. So the first character we're going to load is the capital H. Now there's a couple different ways that we can go about this, and I'm going to show you how to use those a couple different ways. So the first thing that I'm going to do is want to see which value correlates to a capital H. So for that, I'm going to reference an ASCII2 table, and I have one here. You can use any ASCII2 table. You can just reference them from a Google search or whatever and be able to pull something up. So as I'm looking at the ASCII table, we take a look at the capital H, which is right here, and the decimal notation for that is 72. This is one case where I'm going to use decimal just because it's going to be easier to reference, but we're going to show several different ways that we can actually use notation for this load A. So what I want to do is load A with that 72. And you would think that you would just type 72 and you would be all set. You would be wrong. And the reason for that is because you need to be very specific in how you tell the compiler that you're looking to load values. What we want to actually do is use something called immediate mode. Immediate mode means that we are taking a value and loading it immediately into that register. And the notation for immediate mode is the number sign. So I'll put the number sign out front there, and we're telling the compiler that we want to load 72 into register A. If I were to admit that, what's actually going to happen is we would be using what's called direct mode. Remember I mentioned earlier the direct page register? So we would have a default value in the DP register of 0, means that we're at reference or memory page 0 in memory. And what we would actually be doing is loading the value of the memory location 72 into that A register, not the value of the ASCII that we want it to represent. Another notation for direct would be, or extended would be, the $sign. But we'll get into that in future episodes. So I'm going to go ahead and load that 72 into the A register. What we can do is we can set up our comments as well as we're getting into this. And I like to leave a bit of space because sometimes the operand field can get quite long, especially when you have longer labels or if you get into push and pull statements. So to add a comment here, what we do is we first indicate it's a comment with a semicolon. There's two ways that you can actually do comments within 6809 coding, which LWASM identifies with, and that's the semicolon or the asterisk. So I'm going to put a semicolon here, and what I'm going to do is I'm going to say we're loading character H into register A. Now you're typically not going to get this verbose with comments, but just for the sake of the tutorial, just want to be a little bit more clarifying in the comments. So we can go ahead and enter. It'll bring us to our next line. And now what I want to do, that I have a value in that A register, is I want to store that someplace. And based on what we had seen before, we want to store this to the text video screen. So what I'm going to do is I'm going to bring that back up, and this is also available for download in the show notes below if you want to use this for your reference. So the first space in our text video space is going to be address 400. So we're going to go ahead and start there. That's at the very top of the screen. So, whoops, went a little bit too far. We can do store A, is the command that we use to store A someplace. And from there, we want to store it in that memory address 400. So because I want to use memory address, what we do is we use the $sign, and we indicate that we want that in address 400. And I'll put a comment there, basically saying we're storing, oops, can't type, storing A onto screen memory. Okay, so that takes care of our letter H. Next, we want to do our letter E. So what we're going to do is go ahead and load E, or load A with the value for E. So if I pull up my ASCII table again, we will see that that's character 69. So I'll go ahead and type in 69. And I'll leave off the comments because we know, based on what we have above, what that's actually going to do. So we're going to store A into the next memory location, which is $401. So rather than type in the entire code right now and have you sit through all that, I just want to show you how this is going to compile and what we have so far. Now, one last statement that we're going to want to include, which is very important, is the RTS statement. And that's basically the return from subroutine. So that's telling the computer that we are done execution of this portion of code and that we want to go back to the code that originally called us. In this particular case, it would be the operating system. So what this should do is it should dump us back out to the OS after it puts these two characters on the screen. So I'm going to go ahead and save this here. And from here, what I'm going to do is I'm going to pull up our command window, and that is going to bring us to, whoops, a little too far. And what that's going to do is it's going to bring us to our profile. And from here, we navigate to the desktop, and we do dir, and we want to go to 6809 assembly code, which is where we have our source code. And as you can see, I have hello.asm there. And what I'm going to do is I'm going to go ahead and compile this. I'm not going to output it to VCC just yet because I want to show you what the output looks like, and we're going to talk about that for a brief minute. So the command to do that is just our batch file, which is assem.bat. We do not need to include the bat because it will script this for us. And we want to include the name of our source file, which is hello. And again, we do not need to put we do not want to put the .asm on as the extension because that's handled by the batch file as well. So without a target indicated, this will just compile and it'll show us the text output to the screen. And there we go. So we did get a successful compile without errors, and this is what it looks like. So I just wanted to give a quick high-level overview of what this output actually is and what's happening here. So as you can see, things are broken out into columns. And this first column here, where you see this 4,000 over on the left, what this is this is exactly what we were hoping for. This is the start of our code, our executable code, as indicated by our org statement, org 4000. So we wanted our first statement to go, our first executable statement to go at 4000. The next column over is where our machine code is located, or some people refer to it as machine language or bytecode, but this is where the machine code is. And what this actually is the statements that we have typed in here into our source are actually being compiled by the compiler and compiled into our bytecode, our machine code. So what we see here are hex values. This first value, there's 2 bytes here. The first one is 86 hex value, and what that actually correlates to is LDA, load A, immediate mode, immediate addressing, and that is the compiled load A statement into our machine code. So 86 is in reference to load A. The 48 is the hexadecimal notation of our 72. 72 is our decimal notation, and that gets compiled to 48 in our machine code. The next statement down, 4002, is, well, first 4002 is 2 bytes further into our machine code. So there were first 2 bytes here. The 4000 plus 2 is 4002. And the first memory machine code is this B7 here. And this B7 correlates to the store A opcode. Next, we have 0400, which is correlated to our 400 memory address, and so on. So that was 3 bytes long, so our next statement would be 4005. And again, we see another load A, this time with our 45, which is the hex notation of the decimal 69. So that's basically what our code compiles into, is this machine code, and this is what's actually being written right here to the binary and to the disk image. So the next column over, what we have is the path where our source code was located, where it was actually being compiled from, as indicated by this statement that I'm outputting from the batch file as well. Obviously, the field is too short to show all this, but that's what this column is here. The next column over is our line column, our line number column, and each one of these lines of our source code is indicated by a line number here. And then this final section here is just our source code output. And as you can see here, it's very well formatted. It's nicely formatted. And the reason for that is because we are consistent with tabs and spaces. And as you had seen in my first video, when we set up our environment, I had set it up where our tabs would be converted to 4 spaces. If we had a combination of tabs and spaces in here, it would be kind of messy. It would be a bit all over the place, and that's why I like to keep it consistent with the formatting. It shows a nice output, and it's easier to debug. And then lastly, what we have here is our symbol table. And the symbol table gets output, and what it does is it shows what our symbols are, the symbols that we use in our source code, and the memory address that they correlate to. So in our case, we have our label in our instruction label field here as start, and that actually correlates to memory address 4000. And as you can see here, that is consistent with what we see over in our machine code section. So it looks like everything compiled okay. If we had issues, what it would basically do is it would tell us that there were compile errors and what type of compile errors we had, and it would reference a line number, and we would be able to go back to our source code and debug from there. So with that being said, I'm going to go ahead and open this up in VCC, and I'm going to just recompile it and say that the target environment is VCC this time. And we should get it VCC pop up and execute the code. And there we go. So it did write the characters to the screen. As you can see, where we used to have an EX here, it is now saying HE, TNDED. He tended. So that shows us that it is working. And what's happening is the assembly language doesn't have anything in it that's basically saying, all right, I want to clear the screen, or to ignore any of the text that's currently on there. If we were to use a print statement, as you are aware, the print would just show the HE, and then it would overwrite everything else on the line. But that's not the case here. We're just basically telling the system to load these character values into memory, into the A register, and store those on the text screen. And it's that raw and that crude that it will do exactly what we tell it to do. So let's go ahead and get back to some coding. We'll add a little bit more to this, and we'll see what the output looks like. Okay, so let's go ahead and bring up our editor. And what we're going to do right now is do a little bit different notation on how we're loading these values into the A register. So initially we started with decimal. One other option that we can go with is we can do hexadecimal. And you do that by using the $sign. Again, you want to keep the number sign in front of that because that is our immediate mode. We want to load the value of this character immediately into the A register. And the hex notation on this would be 48, as we see here, as the compiler had indicated. So what we could easily do is just change that to a 48, and it would produce the same output. Another way that we can do this with text characters, which is a bit easier, is we can actually indicate the character itself. And the way that we do that is with a single quote mark. So if I use a single quote mark, I type a capital letter H, and it's optional, but because of the way that I've got the formatting, the user-defined language formatted, we're going to close it with another single quote. And that right there is going to be much easier than referencing our ASCII table each and every time. So what I'm going to do is I'm just going to go ahead and continue to populate this with our characters. And I'm just going to copy and paste, make it a bit easier on us. And we'll change the formatting in a second. Oops. And as you can see, one of the nice things with the Notepad++ and the formatting that we're using, it's trying to do code complete for us as we're typing these commands, which makes our lives a little bit easier. So using Notepad++ versus a text editor is a little bit easier in this case, or standard text editor, I should say. And I wish I could type today. All right, so what we've got here is hello, and then we've got to increment our memory locations as well. So we got 401, 402, 403, 404, and what we want to do here is we want to do a space, and that's 405. So I think I've got that right, 401, 402, 403, 404, 405. Okay, so that looks like it should work. So what I'm going to do is go ahead and save this. We'll come back out to our command line, and we'll go ahead and compile this and dump it directly to VCC. And there it goes, it worked. But as you can see, there's a little oddity here. We had indicated that we wanted a space, but we've got this black box here. So you might be asking yourself, what's going on there? I thought we indicated that we wanted a space. So in order for us to see exactly what's going on, what we need to do is see what this actually compiled to. So that statement is right here, and this actually said, all right, load A with hexadecimal value 20. Okay, that seems pretty fair because 20 represents a space. If we pull up our ASCII table, we can come down to 20, which is actually 32 and decimal, and we can see that it's a space. We're like, okay, that makes sense, but why did it show a black box? Okay, folks, so I had a weird interruption there earlier in the day as I was trying to do the video. Windows Update started running in the background, and it really bogged down my system. So I had to stop the video, and I'm picking it back up now this evening. So if you see the screen looks a little bit different, that's what's actually happening. So what we're actually trying to do is figure out the mystery of the black box and why we don't have a space there where it should be. So in order to do that, what I was going to do is write a little basic program to show you exactly what's going on. For those that have programmed in Cocoa Basic, you know that if you do print character $32 or 20 hexadecimal, that you should see a space. So what I'm going to actually do is I'm going to poke values into memory instead of doing print character $, because that's essentially what we're doing with the store command. So the store is actually analogous to poke, so poking the values into memory. So I'm just going to do a little loop here for C equals 0 to 255, which will give us the full character set. I'm going to do a poke, and we're going to start at memory address 400 plus C and the value of C. So basically we're going to start at memory address 400, which as we know is the upper left quadrant, upper left hand side quadrant of the screen, increment by C and poke the value of C into that memory location. So we'll do 40 next, 50, go to 50, and we'll see what this produces. And there we go. So if we take a look at what's been outputted here, as we know, there's 32 columns across. So we start at 0, so this over here where we have the left arrow would actually be character 31. 32, which is hexadecimal 20, is this black box. So that's what we're actually seeing, is the Cocoa font set from the VDG. We're actually poking 32, or hexadecimal 20, which we see right here. Where did we load it? Right here. Address 4019, or actually 401 or 4020. That's what we're seeing, is this is the value 20 that we're poking into this location up here. So this black box is actually being poked into memory. What we actually need to do is this value here. So if we go 32 across, this value here would be 95 decimal, and then this would be 96. So if we modify our code to poke the decimal value of 96 or store 96 into that memory location, we should be all set. So let's go ahead and change that. So I'm going to go ahead and stop the execution of my code, and we're going to pull up our editor And down here where we had a space, what I'm going to do is change that to decimal value 96. So I'm going to go ahead and save that. And from there, what I'm going to do is do another sem on this. Target VCC. And there we go. So we have our green space where we used to have our black space. And if we go back to our code, our source output, we can now see that we are poking or storing, or loading, I should say, load A with the value of hexadecimal 60, which is decimal value 96. So that solves that issue. So we're going to go back and we're going to edit some more code to finish this up. But before we do that, one of the things I wanted to do is show you how we can use the XIndex register to make our lives a little bit easier here. Instead of trying to keep track of every single memory location and adding one to it each time manually, we're going to do that with the X register. And the way that we do that is I'm going to insert a line here at our start that we're going to load X with the start of our video space, which is address 400. And I have the number sign in front there because, again, we're using immediate addressing. So what I want to do is load the value 400 hexadecimal into X. If I had left off the number sign, we would have been doing extended addressing, and what we would have done is actually loaded the value of what's stored in memory location 400 into X. So just want to make sure that as you're going through and doing this coding that you're using the right addressing mode and that you're using the right notation, or else it's going to yield results that you're not expecting, and it gets to be a challenge debugging. So as you're going through this, just be mindful of that, and you're going to run into these issues. It's just going to take practice and you actually coding for you to learn this and really understand what's going on. So from here, what I'm going to do is every place that I have store A in a specific absolute memory location, I'm going to change that to a relative location by using the notation comma X. So we're going to store that value of H into hexadecimal address 400. But what I also want to do is I want to increment that memory location as I leave this instruction. So what we do is we append a plus to it. So what that's actually doing is it's storing the value of A into the X memory location, which happens to be 400, and then it increments X as it leaves. So what's going to end up happening is at the end of this, it's going to be memory address 401 the next time we want to use and reference X. The equivalent of this would be poke A, or poke X comma A colon X equals X plus 1. So that's effectively what we're doing. Storing the value of A into memory location X, and then incrementing X as we leave the instruction. So I'm going to do this for each location that we're using an absolute memory location, and we're just going to continue to increment this as we go along. So each time X is going to go up by 1, and it's going to yield the same result. And I'm going to show you why I do this. And one thing I should note is the compiler and the Notepad++ here will take both capitals as well as lowercase, uppercase and lowercase for our instruction codes. It's a matter of user preference. You can go either way. I prefer the lowercase. It's just a little bit easier on the eyes, and to me it's not shouting the commands at you. But you can go either way, and you don't have to be consistent with it. It's your own personal preference. One thing I do want to mention, though, is as far as the labels go, they do you can use upper and lower case on those, but it will matter as you're going through the code. So you want to make sure that you have consistency among those. So here where I have a start that is capital S and lowercase rest of the word, I do the same down here. If I were to change that to that, it would be something completely different. So you want to make sure that you have consistency along your labeling. Okay, so I'm going to go ahead and save and compile this, and I'll show you that it should produce the same results. And there we go. So what's really nice about this is we can change fairly quickly and easily where that hello is actually being printed. So to give you an example of that, what I'm going to do is I'm going to pull up our memory map again, open this up in a PDF viewer, and here we have address 400 is where we're currently outputting to the screen, but because it's overwriting the disk extended color basic, or in our case extended basic, we haven't set up our VCC for disk use yet. What I want to do is I want to write it to the middle of the screen, so we're not overwriting this and making it difficult to read. So all I have to do is I have to go into my source code and modify my X register to load initially with 500 instead of 400. So we'll go ahead and do that right now. Change that to 500. We'll do a save. We'll assemble and open it to VCC, and there we go. So we're now seeing that in the middle of the screen. Much easier than us going back and modifying every single absolute address as we were writing our code. So starting with index addressing makes it very easy. What we're going to get into in the next video is how to do index addressing for loops, and it'll illustrate how much easier it is to actually write text to the screen. And what we're going to be doing is the equivalent of data statements, where we're actually reading data in from a memory location and storing that on the screen through a loop. But we'll get into that into the next video. So what I'm going to do here is I'm just going to go ahead and finish up our hello world, and we'll take a look at to see what the results look like. Okay, and there we go. We've finished typing in our code. So I'm going to save it here, and we're going to go ahead and execute the code. And there we have it. Hello world. We've written our first assembly language hello world app. So I'm going to leave it at there for this video and this episode. Next time, as I mentioned, we're going to get into how to write text strings to the video screen, the video text screen, at a much easier, more efficient way of doing it. It's going to involve loops. It's going to involve a couple loops, actually. We're also going to get into how to use loops to actually clear the video screen. There are ROM calls that we can do to do that. I'll show you that as well, and I'll show you the difference between the two. So there you have it, folks. Congratulations, you've written your first assembly program. Okay, folks, thanks for stopping by, and until next time, take care from Long Branch Never.